In this next set of videos, we're going to go through the titration of a weak acid with a strong base, acetic acid with NaOH. But before we do, we need to go through a little bit of preliminaries. The Ka value for acetic acid is 1.8 times 10 to the negative fifth. We're going to use that, but we're also going to use pKa. And pKa is defined as the negative log of the Ka, and that's equal to 4.74 for acetic acid. Now remember, pKa measures the acidity of a compound, whereas pH measures really the acidity of a solution, or how much H plus is in solution. Well, so what does Ka mean? It means that if I take acetic acid, now this is acetic acid, but I have a hard time writing it because I like to write it as an organic chemist. So I'm going to shorten it a little bit and call it HAC. Just makes it easier. So I'm going to take HAC and put it into water. And when I put it into water, the water acts as the base, picks up the proton, makes the conjugate acid of water, hydronium, plus acetate. That is the equilibrium expression for a Ka. Now that has a value of 1.8 times 10 to the negative fifth. Now I'm going to just do a little bit of work. And if I take AC minus and flip this over, H3O plus, I will get HAC plus water. Well, this is a reaction you would have run in chapter 4, say, where we're working on stoichiometry. Now, this has a value, this is a Ka, 1.8 times 10 to the negative fifth. But when we flip this over, let's just call this a K for that. That's going to be much, much greater than 1. That value will be 5.6 times 10 to the positive fourth. So I want you to think of anything like this when K is much, much greater than 1 as really a straight up stoichiometry reaction. And we're going to use a stoichiometry chart to count the moles here, whereas with an equilibrium, we're going to use an ice chart. Now the difference with the stoichiometry chart is you have to think about our limiting reactant. There's no limiting reactant with an equilibrium because you're always going back to make some of that. Okay, one of the problems with all this titration stuff is that all the reactions look alike. Now I'm going to take acetate and put it into water. This is not the same reaction as this. This is a stoichiometry reaction. This is an equilibrium. When we put it into water, we're going to make HAC plus OH minus. This is defined as the Kb of acetate, and its value will be Kw, which is 10 to the negative 14th, over Ka of acetic acid. And so this is 10 to the negative 14th over 1.8 times 10 to the negative 5th, and this is equal to 5.6 times 10 to the negative 10th. Now, why do I do this? Well, I'm going to flip it over. And I'll take HAC, our acetic acid, plus OH minus, and this is the reaction we're going to do in our titration. And that makes H2O and acetate. And this value, this K, will be much, much, again, greater than 1. And so this reaction will be a stoichiometry chart. And we're going to use this reaction to count our moles and then put it into the Henderson-Hasselbalch equation to find our pH. So now we're going to set up our reaction. I'm actually going to take the Kb and put it up in the right-hand corner. We're going to use this reaction later. So I'm just going to save it for now, and then I'm going to clean up our workplace right here and then draw our experiment. Okay, so here's our experiment. I'm going to draw us a burette. Ooh, that looked a little bad, but there you go. There's our burette. And into our burette, we're going to put 0.10 molar NaOH. Now we'll set up our beaker underneath. Ooh, there you go. And put in there 25.0 mils of 0.10 molar acetic acid vinegar. Everybody's done this reaction in their intro chem class. And then instead of using an Erlenmeyer and phenolphthalein, we're going to put a little spinny bar in here. And so it's going to be whirling around. And then we'll set up a pH probe right here. So this will go to our pH meter. And then here is the chart we're going to develop. We'll have milliliters of OH minus added. And then over here in our, oh, that was really ugly. Over here, I'll use a line, much better. We will add our pH, and we'll be calculating. Here's the milliliters we're going to do: 0, 10, 12.5, 20, 25, and 40. As we go down, I'll try to put some notes on the side as we use this. Now, granted, when you set up an experiment like this, you usually measure the pH, not calculate the pH. But we're going to go through this step by step so you understand what's happening as the reaction goes forward. And then once you know what happens as the reaction goes forward, when you actually have reactions that have unknowns, you will be able to solve them. At least that's the idea here. So the first step is to find the pH just as you set up the pH probe into your solution of acetic acid. Well, this at 0, you're going to just use the Ka of acetic acid and an ice chart like you did in chapter 14 of Zumdahl, which is what we use in our book. So that step would be just taking my HAC as we've done before, putting it into water and making H3O plus and AC minus, and we're going to go straight to the E. So this is 0.10 minus x squiggly x and x squared over 0.1 minus x, and we can throw away that x because it's small compared to 1, because there is 4 powers of 10 difference between the Ka and the initial concentration. So 1.8 times 10 to the negative 5th. We've done this so many times before, but let's make sure you get it. So when you're done, you solve for x. And let me make sure I got it right in front of me. X turns out to be 1.34 times 10 to the negative 3rd. And your pH better be between 2 and 3 because you have 10 to the negative 3rd. So pH is equal to 2.87. And that's before you even start. Now, as I said, you're not going to be calculating this. The pH meter would read that. Now, dump in 10 milliliters of our NaOH. Okay, now it's down to there. That was sort of cute. And so now we're going to use this stoichiometry chart to count our moles. Before we start, let's make sure we understand molarity is equal to moles per liter, but it's also equal to millimoles per milliliter. So whenever I use titrations, I usually count in millimoles. So millimoles is equal to molarity times milliliters. And so now this amount of millimoles will come from right here, 25 times 0.1. So you have 2.5 millimoles of acetic acid. After you've added 10 milliliters of 0.1 molar NaOH, you've added 1.0 milliliters of OH minus. Now, this is our limiting reactant. So it all goes away. So we're going to lose it. So lose it. And then who cares about water? It's being just made in water and 0.1. So you end up with 1.0 millimoles of acetate, 0 OH minus, and 1.5 millimoles of acetic acid. Now this is where Henderson-Hasselbalch comes in. So if you look, Henderson-Hasselbalch is the equation that comes from Ka. So if you take the expression for Ka right here, which looks like this, and I'll go through it, Ka is equal to H3O plus times AC minus over HAC And amazingly so, just take negative log of both sides. Negative log of the Ka is equal to negative log of the H3O plus. And I'm going to separate out this ratio minus log of the base, AC minus, over the acid, HAC. And of course, this is pKa, measuring the acidity of a molecule, is equal to pH, measuring the acidity of a solution, minus the log of, let's just call it generic base, over acid, HB. Let's put a minus there. Now, we usually want to find pH, so we're just going to rearrange this. So pH will be equal to pKa plus the log of the base over the acid. That is Henderson-Hasselbalch equation. And I use it whenever we're doing a titrations. It makes things simpler because this ratio can be in millimoles or it can be in concentration. So I tend to use Henderson-Hasselbalch in what's called the buffer region of a titration. Okay, so we can just plug in what we have. The pH will be equal to the pKa of acetic acid, which we found up here is 4.74, plus the log of the millimoles of the base, which is 1, over the millimoles of the acid, 1.5. And when we plug that into our calculators, we're going to have a value less than 4.74, and it ends up being 4.56. So this will go right here. Now, when we go to the next point at 12.5, we'll clean up our workspace right here. So the only thing, this doesn't change because that's defined by how much we started with. We're going to be at 1.25, and then this will start at 0. We lose 1.25, still the limiting reactant, 1.25, and then add 1.25. So this is what's called the half equivalence point. When you're actually doing a titration, you don't know where it is because you don't know where the equivalence point is. So when we're done with this, over here, it will be log of 1.25, I'll fix this, over log of 1.25. So log of 1 is 0. So, and at this point, our value is 4.74. So right here, 4.74, that's what's called the half equivalence point. So anywhere in this region, you're going to use what I call the stoichiometry chart plus Henderson-Hasselbalch to find the pH. This region right here is called the buffer region. Whoa, what happened right there? Okay, so we're going to clean up our workspace one more time and then add 20 mils of the OH minus. So you should go and try that and see what you come up with using our stoichiometry chart and Henderson-Hasselbalch. See, I'm waiting for you to finish, so I'm going to give you some time. Okay, so let's put in, this will be 2.0, so still limiting reactant, 2.0 minus 2.0, and then plus 2.0. And so we get 2 on here, so the base is going to be 2.0, and the acid is going to be 0.5, so it's just log of 4. And so when we finish that, that answer will be 5.34. So that completes the section in the buffer region on how to find the pH.